Hi, this is Professor Fernandez, and in this video we will be talking about Module 3 of Lesson 16. So the topic here is Green's theorems, and I say that with a plural even though Green's theorems are usually presented as just a single theorem, Green's theorem, but I do want to separate them here as we've been separating the notions of circulation and flux throughout this lesson and the previous module specifically. So let's just go through the theorem. There'll be some new terminology that I'm going to show you down here. So the presumptions, the hypotheses of this theorem parallel those that we had seen when we defined circulation and flux in the previous module, Module 2. So C here is a curve that is simple. Remember, that means it doesn't intersect itself. Closed, piecewise smooth, and it's a plane curve as usual, oriented counterclockwise. We're also going to now suppose that, when I draw the curve C, because it's closed, it starts and ends at the same points. And we're going to assume that the region that it encloses, in other words, all of this, call it D, we will assume that this region is connected and simply connected. So those are the new terms. So I'm going to show you what that means here in a little bit. I want to read through the rest of the theorem to show you sort of the big connection that Green's theorems make. Suppose that F is a vector field, two-dimensional vector field, with f and g having continuous first partial derivatives on some set containing C and D. So we're thinking about, an open set here that contains all the actions, so to speak, the curve C and the region D it encloses. Okay, then we have the following conclusions. So this is Green's theorem, the circulation form. Remember that this integral of f dot t ds was the circulation. You'll notice that there's a little symbol here that looks like a circle through the integral. That just is there to remind you that we are assuming that C is a closed curve. Okay, so this is the circulation. Green's theorem says that it equals this specific double integral. And what's really interesting about this double integral is that it involves the curl. We have teased in previous videos and in previous lessons that the curl might have something to do with rotation and circulation. So we will talk much more in a few minutes about how Green's theorem gives us exactly that picture of the curl. Okay, here's Green's theorem, the flux form. The left-hand side is what we defined the flux to be in the previous module, Module 2. Green's theorem relates that to the divergence of the vector field. Similar thing there. We had talked before in previous videos about the divergence, giving us some notion of flow outward or inward sources or sinks. And Green's theorem relates that to the flux that we talked about in the previous video. Okay, so what I want to do first is go back to the new terminology in this definition, and then we will do an example, and then I'll tell you all about the insights that Green's theorems contain. So let me go back to this new terminology here, connected and simply connected. Again, I want you to have a picture here of the curve, the blue curve here being simple, pathwise, piecewise smooth, oriented counterclockwise. So this is a nice picture to have. And closed. So that's the curve. The region it encloses could look very different depending on what assumptions you make. So here's a little diagram that I've prepared for you. So the region that we're after in Green's theorem is this one, this first one. So we want the region to be connected and simply connected. So connected means that the region we're looking at is just one chunk. So over here is an example of a region that's not connected, two chunks. Same deal over here. This region is not connected, so it's two different chunks. We also want the region for Green's theorem to be simply connected. What we mean by that is effectively that it has no holes, right? So this region does not have any holes. This region does have holes, and this region does have holes. There's a slightly more technical definition of simply connected, but basically the notion that the region has no holes will be enough for us. So if I had to sum up what a connected and simply connected region looks like, the way I think of it is you have the unit circle, let's say, or a disk where it's filled in, and then just, deform it a little bit. So that is a connected and simply connected region. So, you can see that this is in some sense equivalent to that if I just move around the boundaries almost as if, if you're making pancakes one day and the batter kind of flows onto the pan, it can get kind of moved around, but, you're not going to make a pancake that looks like this. So this is what I imagine to convey when we're talking about a connected and simply connected region. Okay, so one blob that may look like a deformed disk. So writing out each side of Green's theorems over here, so I'm referring to these equations, we get these representations of them. So let me just go through this in a little more detail. This over here, remember, was when we wrote out the circulation in terms of the functions f and g, the components of the vector field. This is when we wrote out the flux in terms of the components f and g of the vector field. And the right-hand side is now the stuff that's kind of new, but not really, because we talked about divergence and curl a couple of modules ago. So remember that the curl in 2 dimensions is just the z components of the curl in 3 dimensions. And the curl in 3 dimensions, dot k, gives us the z component of that 3-dimensional curl. That is the integrand of the circulation form of Green's theorem. So that's gx minus fy, partial derivatives. The divergence in 2 dimensions is just differentiate f with respect to x, fx, plus differentiate g with respect to y, gy, and then add them. So that is the integrand for the flux form in Green's theorem. Okay, last note that I want to mention about Green's theorem. This is a theorem that has many proofs depending on how the region that you're looking at is constructed. For example, we could be dealing with a type 1 plane region, like that, or we could be dealing with a type 2 plane region, like that. So there's different ways that the region D might show up, and therefore that affects a little bit of how you do the proof. This Wikipedia page, if you click on this, has one of those proofs in it, and you can kind of see what's happening, and I'll mention in a little bit basically the gist of the proof. But I did want to mention that much easier to see is that you can derive one version of the theorem from the other. So for example, if you start with a circulation form, which is this one, and you look at the vector field negative g and f, what would happen? Well, so this this first component here is negative g, so that would give you that portion. And this second component here is f, so that gives you that portion. And then negative g is the first component. You put it in here, and that gives you, let's see, oh, wrong place. This is the first component, and so that goes over here, and you put in negative g, and that gives you minus plus the derivative of g with respect to y. That gives you that. This is the second component, so you put it in here, and that gives you the derivative of f with respect to x, gives you that. So conclusion, if you apply the circulation form of Green's theorem to this vector field, you get the flux form. You could also play a similar game the other way around. You could apply the flux form to a specific vector field to get the circulation form. So it's for this reason that sometimes Green's theorems are referred to as just Green's theorem, singular, because you can get one from the other. But again, I wanted to separate them because we've been talking about circulation and flux. Okay, so then back to that small comment I mentioned that I was going to make about the proof of Green's theorem in general. The proofs usually what they do is that they will take one of these integrals, line integrals, and they will try to show that it's equal to one of these double integrals. And then they'll take the other part of this integral, and they'll show that it's equal to the other part of this double integral. The one thing I want to mention there, the one sort of somewhat deep insight that's going on here in terms of the proof of Green's theorem, is that notice that, on the right-hand side, let's just take the divergence form here, I am effectively integrating twice the function that's a function that's already differentiated. So, when I go to do the dx version of this integral, I'm differentiating f with respect to x. So again, kind of like what happened in the previous module's video when we talked about path independence, I'm going to end up getting at some point, one of these is going to be an integral of the derivative of the function. and that's going to give me back just the function, right, from our fundamental theorem of calculus. And then I'll be left doing one last integral of the function. You can see how that's effectively this, an integral of the function. So that is basically a very quick, very rough sketch of how the proofs go. They use this basic fact and structure of Green's theorem to help prove it. Okay, there are many, many more insights contained in Green's theorem, and most of this video actually is going to be me helping you understand what those insights are, because at this point, honestly, we've done all of the work that is required to calculate each of these sides of Green's theorem. So at this point, Green's theorem is, certainly a deep theorem in the sense that it relates these two sides together. But in terms of calculating and verifying Green's theorem, we will just do more line integrals and do more double integrals, which we've done certainly enough of. So I am going to do an example to show you how that verification would go. So here I am choosing the same two vector fields that I've been working with throughout this lesson, just again to anchor our understanding in some tangible vector fields that we can always go back to. So this is the same curve as usual. I'm going to assume that C is a unit circle centered at the origin, traced out counterclockwise. There's the parameterization. And I'm just going to remind you what we had found in previous examples. So we had found that this vector field had a positive circulation, and we found that it had zero flux. And we went through in previous videos and kind of looked at the vector field itself and gleaned that from its plots. We found that this vector field had no circulation and had positive flux. So remember, this was kind of like the explosion vector field that kind of went out from the origin radially. And this was literally the rotational vector field that just went around the origin that way. Okay, so what I want to do in this example is to confirm Green's theorem for the two vector fields that we had just talked about. To do that, I am going to go back to the theorem itself, just to remind you of the hypotheses and make sure we check everything. So, is our curve simple, closed, piecewise smooth, a plane curve, and oriented counterclockwise? A lot of stuff to check, I know, but our curve here is a unit circle oriented counterclockwise. It does not intersect itself, so it is simple. It is definitely closed. It is nice and smooth, not just piecewise smooth, and it is traced out counterclockwise. So those are the four requirements: 1, 2, 3, 4, and plane curve, yes, but we've been doing mostly everything in the plane. So check, we satisfied that hypothesis. Now let's look at the region that C encloses. Let's call it D. Is it connected and simply connected? Basically, does it look like this, one blob of a pancake, or a deformed unit circle, unit disk? And yes, so the region that our curve C encloses is in fact a disk. So that is connected and simply connected. Connected, simply connected. Great. Next hypothesis, set of hypotheses. The vector field F is two-dimensional. It is. And F and G have continuous first partial derivatives on some open set containing C and D. Well, so here this is F, this is G, and here this is F, this is G. These are all, simple, in all cases, linear functions. So they are actually continuous everywhere, defined everywhere, differentiable everywhere. So we satisfied that hypothesis also. So this is one thing I do encourage you to do, which is, I always encourage you to do this, but specifically with Green's theorem, which is to check the hypotheses. It is very easy to just apply any one of these two equations or results and convert back from one to the other without checking the hypotheses. And this is one theorem that has lots of hypotheses, because things have to be effectively kind of nice before you are able to make these connections. And if you end up just using these equations without checking the hypotheses, you might find yourself, running into some contradictions when you calculate either side of the equation and they're not equal. So I do recommend you checking the hypotheses before using this particular theorem. Okay, so now let's go on and actually verify Green's theorem for these two vector fields. What do I mean by verify? What I mean is I want to calculate each side of the equation and compare them. They should be the same. So I'm going to start on the left here, and we have this vector field that we're going to look at. Let me keep the color here in blue. So I've already written out over here what we're looking for. The circulation form of Green's theorem tells us that on the left-hand side, the circulation, which was 2 pi, should equal this, which is the double integral of the curl, the two-dimensional curl. So I need to calculate gx and fy. So let me go up here and actually just calculate all of the partial derivatives. Fx, well, f does not depend on, so how did I get f and g? Let me back up here. This is f and this is g. Okay, so now fx, this does not depend on x, so that's 0. Fy is -1. Looking over here now, gx, this is 1, and then g does not depend on y, so gy is 0. So now I can put that result in here. Gx here is 1 minus fy, 1 minus -1, so that's 2. And then I see that I can just pull this 2 out, and then I'm taking the double integral of 1 dA. Remember, this is one of the properties of our double integrals. This just gives us the area of the region D. The region D here, as we saw up here, is the unit disk. So the area of a disk is pi r squared, but the radius is 1, so we just get pi. So this area of the region D is pi, so I get 2 pi. So indeed, that does match with what the circulation value we had gotten earlier is. So great, this one checks out. And now let's look at the flux form of Green's theorem for this particular vector field. Here I'm going to use the divergence as the integrand. So I want to calculate fx plus gy. Fx is 0 plus gy is 0, so this is 0. So the integral is 0. So again, that also checks out. Great. So we verified Green's theorem, both flux and circulation form for this vector field. All right, so now let's do that over again for the vector field over here. This is the explosion one. And let's remind ourselves that we had calculated 0 and 4 pi for the quantities that are going to be on the left-hand side, the circulation on the left and the flux on the left of Green's theorems. Okay, so now we're going to go down here and then calculate the partial derivatives. This is little f, this is little g. There we go, and then let's just take the partial derivatives. Fx is 2, Fy is 0, f does not depend on y. Gx is 0, there are no x's in here, and then gy is 2. And so now I go down here. So starting again with the circulation form of Green's theorem, we had found the circulation to be 0. So that's the left-hand side. And it equals the double integral of the two-dimensional curl, which is gx minus fy. So gx here is 0, minus fy, that's also 0. So I get 0, and that makes sense. Verified that part. And then now we go to the flux form. The flux form is, on the left-hand side, we had calculated this to be 4 pi. So there it is. And it's the double integral of the two-dimensional divergence. So fx plus gy. Fx is 2 plus gy is 2. That gives me 4. Similar thing here. I pull the 4 out. I'm now integrating 1 dA. This is the area of the region D. Back to that same calculation. D is a unit disk. Its area is pi. So this is 4 times pi. So once again, verified that. Great. So at this point, we've verified both forms of Green's theorems for both of these vector fields. And, this is roughly how these calculations would go. You can see that I've effectively split up this calculation across multiple videos and multiple lessons. So, if you were asked to verify Green's theorem or theorems in a practice problem or homework or something, it might take you a while because there might be a lot of stuff to calculate. For example, have to calculate a circulation. That would involve parametrizing the curve and just calculating the integral, the line integral. And then you might also have to calculate, to verify the circulation version, the two-dimensional curl. And then the double integral. That might get a little tricky depending on the region of integration. And then finally, you would want to verify that those two quantities, answers you got, are actually equal. And of course, before all that, as I mentioned earlier, you'd want to verify all the hypotheses of Green's theorem. So this is, again, one of the reasons why this is at the very end, toward the end of the course. There's lots of concepts and contents that we've studied now that helps us actually do all of, each side of Green's theorem and do the verification. Okay, so that's the only example that I want to go through. You can see that those examples might take a while, but hopefully they illustrate each side of Green's theorems. And then now I want to talk about what Green's theorems can tell us and what insights they contain. So Green's theorems spawn a multitude of connections and interpretations. I do mean multitude here. I'll mention some of those on the next page, but I will also mention that there are many that I won't talk about just for purposes of time. So before discussing those, let me briefly talk about what Green's theorems tell us about curl and divergence of a vector field. We've had these notions that perhaps curl measures rotation, perhaps divergence measures expansion contraction, loosely speaking. So let's see how Green's theorems can actually give us that interpretation, but much more finely described. Let's assume again that we're dealing with two-dimensional vector fields. And I'm going to suppose that F satisfies all the hypotheses of Green's theorems. And I'm going to take as my curve, for Green's theorem's purposes, a circle of radius r that is contained in this region that the vector field satisfies all the hypotheses over. I just noticed that I use the same letter here for D, and I'm not using the D in the sense of the region contained in the curve. I'm using here the D in the sense of both of these things are contained in some region D. So that can be a little confusing, so I think I will change that. Let's just change that to U. U kind of contains the curve C and the region D, which the curve C encloses. Okay, so suppose now, just for the sake of argument, to make things a little easier, then we'll move away from it. Suppose now that the two-dimensional curl is constant. In other words, you get a number, which is exactly what happened over here in both these cases, right? This two-dimensional curl was 2. This two-dimensional curl was 0. So I'm kind of extrapolating, generalizing from this example we did to give you some more information about what Green's theorem tells us about curl and divergence. Okay, then by the circulation form of Green's theorem, this is the circulation around the curve CR. Again, just a circle of radius r over here. Let's put that in a different color. And the two-dimensional curl is a constant, so that's the integrand. I can now pull that out of the integrand, and then I'm left with C times the area of D. And again, D here is the region enclosed by the curve. Okay, so then what do? I can realize that D is a circle of radius r because C is a circle of radius r. So I should say D is a disk, a disk of radius r. In other words, it's this whole filled in thing. And the area, just like we talked about with the example of that, is pi r squared. So A of D is pi r squared. So I can solve here for C and divide by pi r squared over here, 1 over pi r squared, and that gets me over here. So C equals 1 over pi r squared times the circulation. If I put back in the fact that C is the two-dimensional curl, I get an expression for the two-dimensional curl. So what does this all mean? Well, this means, if I literally read it off, it means that the two-dimensional curl is 1 over the area of the disk enclosed by C sub r times the circulation of the vector field along C sub r. So, that may or may not mean anything, but we are going to push it to its limit at literally in a minute. If we start here and we take the limit as r goes to 0. In other words, as the curve that I'm considering over here gets smaller and smaller and smaller and smaller in radius, then what happens? Well, because on such small domains, the curl of f doesn't vary much, we can actually move away from the assumption that the curl is constant. We can move away from this assumption up here, that the curl is constant, and we can now go back to the assumption that the curl is, whatever function it is. On such a small domain, because we've assumed that all the partial derivatives are continuous for the components of the vector field f, the curl, when you calculate it, it's going to be some other functions that are going to be nice and smooth and continuous. So we are going to have on very, very small domains, those functions are not going to vary. We're not going to expect crazy oscillations. So they're going to be relatively constant. So we're kind of back to this assumption. So over small domains, the curl of f doesn't vary very much. And this argument literally goes through in the limit. And actually, in some books, this is, the definition of the curl. It is defined literally in terms of the circulation. So what does this teach us then? It tells us that the curl of a vector field measures the local tendency of the field to rotate. So before discussing those little caveats in there, let me first say that this vindicates our original hunches, that the curl is measuring something about rotation. Really, we have now discovered that that's true, and we're honing in on this notion of local. So what I mean by local here, I mean local means over small regions with small areas, right? That is exactly what we did here in taking the limits as the radius of our curve C sub r went to 0. So if you imagine a vector field then that maybe looks like this, it maybe has a bunch of crazy arrows everywhere. This is our vector field. Whereas before we had the hunch that the curl maybe measures the rotation of the whole thing. Actually now we've, come across an object that does that measurement better. That's the circulation. That's literally what I've done here. I've drawn a curve oriented that I could measure the circulation around, and that will tell me around this curve how much or not the vector field is rotating. But the curl itself is really a measure of local tendency. So if I were to draw a tiny little circle here, and I've only drawn a few vectors in this fictitious vector field, but there's a bunch of other vectors that might be crossing over here, who knows? Then around that tiny circle, I am getting a measure of the tendency of the field to rotate when I calculate the curl of the vector field. So this is one of the sort of nice and deep insights that Green's theorem can help us with. So the next thing, what if I do this all over again, but for the flux form of Green's theorem? So let's restart. Suppose now that the divergence is constant. Then by the flux form of Green's theorem, this was the flux. It equals the double integral of the divergence, two-dimensional divergence. I'm assuming that's constant, so I pull that out. So again, I have a situation where I can replace A of D by the area of the disk, and I divide by A of D both sides, and I get this. I put back in my divergence, which was equal to C, and I get this. And once again, I make the same argument. The divergence is the sum of derivatives of the components of the vector field F. The components of the vector field F we assumed had continuous first partial derivatives. So when I calculate the divergence, I'm going to have continuous functions. And over very small domains, continuous functions don't vary very much. They're relatively constant, so we're back to this assumption. So if I take the limit as r goes to 0 and I make this CR domain, this disk really tiny, then all of that kicks in and I can justify once again claiming that the divergence, constant or not, is the limit as r goes to 0 of this little disk times, or 1 divided by the area of this little disk times the flux. So a conclusion from this one: the divergence of a vector field measures the local tendency of the field to expand or contract. Remember, that is what the flux was measuring, right? In the fluid case, how much of the fluid is flowing out of or through the curve C or into the curve C. So positive flux or negative flux. So this is really nice, right? The Green's theorems have given us a really precise and very intuitive understanding of the curl and divergence of vector fields. So to summarize, we can loosely think of curl as the circulation per unit area, right? Again, if we go up here, this was the curl, and this is the circulation. We're dividing it by the area. So circulation per unit area, the circulation density, you could say. And the divergence as the flux per unit area. Here is the flux, dividing it by the area, flux per unit area, the flux density, if you will. Great, there's lots and lots of other connections, as I mentioned earlier, between Green's theorems and curl, divergence, and other concepts. This actually is a table from Calculus Early Transcendentals by Briggs, Cochrane, and Gillette. I think this is an excellent book to learn calculus from if you want all the nitty-gritty details. What's really nice about this table is that it summarizes many of those connections well. So I just want to go through the table here. So the first part is talking about circulation/work integrals. Remember all the different forms that we had for this when we first introduced vector line integrals. I'll zoom in a little bit here. This is the form that we had talked about. And then we quickly showed that it's equivalent to this, which we now recognize as the circulation. So, as you know, when the curve C is closed. And then this is the writing out the, when you use a parameterization and you write out f.dr or f.tds, this is what you get. Okay, so then now here are some of the nice ways to organize what we've learned across these past few videos and lessons. Suppose the curve C is closed, and suppose that the vector field is conservative. Then this is what we talked about in the previous module. The line integral of f.dr is 0. Because remember that if the vector field is conservative, the line integral of the gradient of the function is just the difference in the starting and ending points of the curve. So this is A, this is B, and this is the curve. If the curve is closed, then it starts and ends at the same point. So this quantity is 0. So that's, and we know that the curve here is closed because we're assuming that in this column. Okay, so that's nice, and that summarizes our path independence of conservative vector fields theorem in the previous lesson. If the curve C is not closed, but f is still conservative, well, that's exactly what I wrote over here. And that's what we had talked about in that theorem of path independence. All right, suppose f is not conservative, and the curve C is closed. Then to calculate this, which is the circulation or work, we can use Green's theorem. And here it is, double integral of the two-dimensional curl, gx minus fy. If the curve C is not closed, and f is not conservative, well, it's not closed, the curve. So we can't use Green's theorem. That's one of the assumptions in Green's theorem. And so in that case, to calculate this circulation, we wouldn't necessarily call it a circulation at that point. We call it more of a vector line integral that effectively means work. So to calculate that, we would just do it directly. So we calculate this right-hand side. And dx is x prime of t dt. That's why there's an x prime here. And then dy is y prime of t dt. That's why there's a y prime here. Okay, and that's basically the story for this part of the table. So now let's look at the flux version. So flux, here we go. This is our definition in the previous video's module. And this is the right-hand side when we actually wrote out what the normal vector was. Suppose that f is source-free. So we haven't really discussed these concepts, this terminology, source-free or not source-free. But long story short, source-free means that the divergence is 0. And not source-free means that the divergence is not 0. So we'll talk about the divergence being 0 first. If the divergence is 0 and the curve is closed, well, the curve is closed, so we're in the Green's theorem hypotheses. And assuming everything else works out, the curve is simple and pathwise connected, piecewise smooth, I should say, and all the other hypotheses are met, then, the divergence is 0. So by Green's theorem, the flux equals the double integral of the divergence. That would be 0. So you get this. And if you're still 0 divergence and the curve C is not closed, well, then this part we haven't talked about. So I would ignore this part. This has to do with streamlines, which is a concept we haven't talked about. So I would ignore for now. As I mentioned earlier, there are so many connections between Green's theorems And I mentioned that we'd only be talking about some of them. But let's now go down here. So what if the divergence of f is not 0, but the curve C is still closed? Great, so we are in Green's theorem land. Then to calculate the flux, we could use the double integral of the divergence. And then what if the divergence is not 0 and the curve C is not closed? The curve C is not closed. Green's theorem's hypotheses are not all satisfied, so I can't use Green's theorem. But I can just evaluate it directly. So this is what we did when we first talked about the flux concept. Great, so I hope that that is a really nice way, and this is in the lesson notes, which again you can download. So this is a nice way, I hope, to summarize most of what we've done, and some even additional information that you can go off and learn. So the last thing I'll say about this lesson is the useful interpretations of Green's theorems that flow, these kind of very intuitive and somewhat real-world interpretations. So here they are. The circulation form of Green's theorem, this is equation 16.1, tells us that the circulation of f along the boundary of the region D, that is the curve C. Remember, we're thinking of the curve C here, and the region D is everything that is enclosed by C. So the circulation along the boundary of the region D, the curve C, is equal to the sum of the curl of f over all points in D. Right? That's literally what this says. This is the circulation, and this is the curl. And remember, if we think about this double integral as a Riemann sum, we are adding all of the curls along every single little area patch of the region D. So that's what I mean here by the sum of the curl of f over all points in D. Thinking of f as a fluid velocity field, thinking of yourself as, maybe standing in a river, and the river is flowing by as you feel it, along your ankles. The circulation form of Green's theorem says that the cumulative rotation of flow inside D equals the net circulation of flow along the boundary. So again, if I think of, this being a river, oops, let me go back here, and there's a bunch of vectors flowing here. This is the, velocity of the stream particles, right? Then you can see that, maybe in here in the region D, there's some rotation going on locally, maybe over here, over here, over here. And then Green's theorem, when viewed this way, says that if I go in and I add up the contributions of all of these little pieces of rotation, this one goes that way, and this one goes that way, this one goes that way, and I add it up over the entire region D, it kind of makes sense that this would be related to the circulation along the boundary. Because, if this one is rotating this way, but this one's rotating that way, maybe they cancel each other out. So as I add and look at all these different rotations through the entire domain G, I'm going to get, or not, some net circulation of fluid along the boundary. And that's effectively what Green's theorem tells us intuitively. And of course, it tells us exactly how to measure that. So on to the flux form. 16.2 tells us that the flux of f through the boundary of the region D, that is across the curve C, is equal to, trying to bring this back up, it won't let me. Okay, is equal to the flux, is equal to the sum of the divergence f over all points in D. All right, so let's scroll back up. Remember, this is the flux form. So this is the flux. This is the flux through the boundary of our region D, which is the curve C. And it's equal to, there it is, the sum, again, thinking of this double integral in terms of the Riemann sums, of the divergence through every single little patch. So the picture here is somewhat like what I've drawn here, but it's slightly different. So here is my curve C. The region D is what the curve C encloses. And here's my vector field, fictitious vector field. I'm thinking once again of you standing in a river, and the vector field is the velocity field. Rather than thinking about circulation, all these little eddies, if you will, that we were looking at here, I'm thinking on the left-hand side here of flow through D, and also eventually through C. So for example, this fluid particle here is moving that way. So maybe if there's no obstruction, it ends up flowing out of C. That would contribute to, in a positive way, to the flux through C. But maybe there are fluid particles that are flowing in the opposite direction. So maybe this one, if unobstructed, would flow, well, I guess that one would flow also out of D. So this one right here. So if unobstructed, this one would flow into D. So that would contribute a little negative flux to the overall flux. And that's the exact idea. As I add up all of these contributions, positive and negative, to the flow through C, I get the net flux. So that gets me back to this interpretation. Thinking of F as the fluid flow, the flux form of Green's theorem says that the cumulative flux of flow inside D equals the net flux of flow across the boundary, which is the curve C. Okay, so I have said a lot in this lesson. This is another one in this video, another video that might be worth watching a couple of times. I try to give you interpretations that are physical in nature, that, next time you go for a swim in a river or in a pool, you might think about Green's theorem and the circulation and the flux form. There's also, I try to give you the connections, mathematical connections, that can help you, for example, if you are trying to calculate the circulation or the flux. It might be possible to calculate instead a double integral. Again, assuming that all the hypotheses of Green's theorem are satisfied. And then, these big takeaways of what curl and divergence can really be understood to mean as these kind of flux, circulation densities and flux densities. And the last one, of course, all of this flows from Green's theorem itself. So making sure, again, that we satisfy all the hypotheses. There's a big paragraph here of hypotheses before we use the actual theorem itself. So that's it for this video, and I will see you in the next one.